Have you ever wondered how scientists track every drop of water that falls and flows through a specific landscape, from mountain peaks to river valleys? Imagine trying to account for every single input and output of water in a defined area, understanding its journey and its impact. It is a fundamental question in water science, crucial for managing our planet's most vital resource. We compute hydrologic balance for catchments by applying the principle of conservation of mass to water within a defined geographic area, known as a catchment or watershed. Essentially, it is an accounting exercise where the total water inflow must equal the total water outflow plus any change in the water stored within that system. This is represented by the core equation. Precipitation minus streamflow minus evapotranspiration equals the change in storage over time. This equation, P minus Q minus Et equals, over dt, is the bedrock of understanding water movement. P stands for precipitation, which includes all forms of water falling onto the catchment, such as rain and snow. Q represents streamflow or runoff, which is the water flowing out of the catchment through rivers and streams. Et is evapotranspiration, the combined process of evaporation from surfaces and transpiration from plants returning water vapor to the atmosphere. Finally, over dt signifies the change in water storage within the catchment, which can include soil moisture, groundwater, and surface water bodies like lakes or reservoirs. The accuracy of this computation heavily relies on precisely defining the physical boundaries of the catchment, usually determined by topography. In practice, computing these components involves various measurement techniques. Precipitation is typically measured using rain gauges or radar systems. Streamflow is monitored with stream gauges that record water level and velocity, allowing for calculation of discharge. Evapotranspiration is more complex to measure directly but can be estimated using meteorological data and models, or through advanced techniques like eddy covariance towers. Changes in storage are often inferred from changes in soil moisture content, groundwater levels in observation wells, or remote sensing data for surface water bodies. An important aspect of this accounting is considering the chosen time period, often referred to as a water year, which typically runs from October 1st to September 30th in many regions to align with seasonal cycles of precipitation and runoff. Moreover, these computations can range from simple lumped models that treat the entire catchment as a single unit to complex distributed models that simulate water movement at a fine spatial resolution across the landscape, capturing intricate variations in topography, soil, and vegetation. Ultimately, understanding how to compute hydrologic balance is vital for informed water resource management. It allows us to predict water availability, assess the impacts of land use changes, forecast floods and droughts, and develop sustainable strategies for human consumption, agriculture, and ecosystem health. This powerful tool provides a comprehensive picture of our water resources, empowering better decision-making for a resilient future.
If you love learning about water, like, subscribe, and keep exploring with us.